Hello everybody, welcome to this video kind of like walkthrough of my article, Don't Be Afraid of Non-Parametric Topic Models. Dive into an easy step-by-step tutorial on how to implement and evaluate a hierarchical Dirichlet process model. Hi, my name is Eduardo and I'm a recent graduate from Duke University's Master's in Statistical Science program, and I'll be moving to become a consultant in a couple of months in the role as a data scientist. So I know there's a lot of detail in the article, and I previously had published high-level foundational material about what non-parametric topic models were, specifically a hierarchical Dirichlet process model was. But I wanted this specific video tutorial to be a place where you can see how this code runs in an actual Jupyter notebook. So with further ado, let's move on. So the first thing that we'll do is we'll load a couple of packages. And here we will load your typical pandas and NumPy, and we will load a couple of other functions, specifically the fetch 20 newsgroup function from sklearn datasets. The reason why we want to do that, I'll mention it in a couple of steps further. Now, since we're going to be handling text data, a good first thing that you want to do is download stop words. You can use the NLTK package to do so, and this, when it downloads this stop words, it downloads it as a list, so you are always free to extend that list with your own stop words. And as I mentioned in the article, it is important to really think about this step, because depending on what your objectives are, you might want to not remove all the stop words, because that might provide you some further information that you might need. In our case, we're okay removing the traditional stop words because we're just trying to analyze documents and figure out underlying topics from this document. So as I mentioned, we will be using the 20 news group dataset. It's a pretty nice toy dataset in that you are able to see what are the true labels of the actual texts that you have. And what do I mean by that? Let me just show you briefly. First, we can download this object news with a fetch function, and then we can build a data frame such that you can see more clearly what kind of information this type of data set has. For example, as I mentioned, you will get the content in this middle, as you can see in this middle column, but you can also get a specific topic ID and a specific topic name. And this is very unique to this dataset because it was constructed in this way, in which the documents that are part of this data have been pretty much broken down into 20 specific news groups, if you want to call them this way, so 20 topics. And these topics tend to be evenly distributed across the whole dataset. So it is a really good model to kind of test how the hierarchical Dirichlet process will perform, and actually kind of use that as a ground truth. However, as I mentioned, this is not obviously available in all the other any other data sets. So the first thing that we might want to do is we want to get this content data, and we can do this by turning it into a list. And then as you can see, the list contains, each entry is like a very long string, which has certain things that we might want to remove. For example, the from is one thing that you might want to remove. There's a lot of emails, so things really that have @ signs you might want to remove. We also see that there's a couple of new lines, for example, that we might want to remove. So that might be two things that we might want to do when we're pre-processing. So for the first part, let's think about first removing the any emails or any new line characters or any single quotes available. You could do this with some list comprehensions and classical regular expressions and using the sub method. And so when you run this and you compare what you get in return, as you can see, the email has been completely removed, as well as like the new lines that you had previously. So that's probably the first thing you want to do. Now, what you can later do is pretty much tokenize your data. And for this, you can use a very neat function from Gensim, which is a topic modeling package. And here, basically, what you want to do is, again, use a list comprehension, and you pass on each string as inputs. You can decide whether to remove accents or not. In the case of this data set, we want to, because we're assuming these are English language documents or data. If it's maybe a French or Spanish language, you might not want to keep that. And then you can also apply some filtering in saying that as you're breaking down this huge string, you might want to only keep those tokens or words that are at least of length 3. So once you do that, this becomes like a list of sublists. So what do I mean by that? Here for example, if I want to get the same data as before, I might choose the second the second entry, or like the third entry in this case, and then I want to see maybe the first 6 tokens. As you can see, right now we have from Thomas Willis, because E got filtered because of the min length, and as you can see, it pretty much breaks it down into its own tokens. Now, before we move along and remove certain things like from, we want to create something called bigrams. By bigrams, this mean pretty much capture co-occurring words. So for example, if we had oil leak, we might want to model it as oil leak together rather than just taking oil by itself and leak as a separate word, because that might come up separately in our topics, and so we might not be able to like construct a better inference or deduction of what a topic means. So what you can use some of Gensim's built-in functions like phrases and phraser that allow you to build these kind of like bigrams. So first we need to initialize these kind of like bigram models using these 2 functions. Here the min count means create bigrams that appear at least in 5 documents, and the threshold pretty much means it's a way in which you kind of like force this model to only give you a certain amount of bigrams. The higher the threshold, the lower number of bigrams you will get. So, okay, now that that's run, the next step that we want to do is we want to remove kind of like the standard and extended words. Here's a quick example of how that might look like. So, for example, in this printout, it just shows you what words would be kept and which one would be removed. The removed ones would be considered stop words. And so things like pronouns normally get excluded, and this is something that we might want to remove in this case. So again, we can use some list comprehensions to keep the same structure. And this is what we get, let's say, for the same data that we've been seeing. As you can see, what got removed is the from. Previously we had the from, and then that got removed. We also got removed subject as another example. So these are other things that we added to the extended stop words that we want to remove. Next, once we've removed all of the stop words, we want to then create the bigrams with the remaining set of tokens that we have. So we can use again list comprehensions using the bigram model that we had previously, and then we can again go and see if there's any like bigrams created on the first 7 tokens of that same document. And as you can see, very very explicitly, Purdue University was actually put together as one single word, and that's what bigramming does. If we wouldn't have done this, Purdue and university would have been different, and we might have had like a different word within the topic. And so this helps kind of like keep some context, if you want to call it that way, in place. Okay, now let's go into word limitsization. So limitsization pretty much means removing the inflection points of certain words, so you can get like the dictionary word as an example. In here, you can see that we have our original kind of like words on the left, and then on the right we have two things. We have first the lemmatized word, and then second the POS tag, which stands for part of speech tag. So in here, this is pretty much signifying that letter is a noun, but for example, written is a verb. And so what lemmitizing does is it turns that kind of like past tense into present tense, like right, like the actual dictionary word. And so this is a very, this is kind of like the correct way to pre-process the words such that you have kind of well structured vocabulary, such that when you're reading out the topics that your model infers, you don't want to have some truncated words and try to figure out what type of meaning, was it past tense, present tense, did it have a different root that compared to other words. And so this pretty much gives you like the actual words that you want to do. However, I want to mention that doing this takes a long time. This is an example function that I created in which I pass the kind of like the word list, the list with sublists with the tokens, and a specific types of part of speech tags. And in this example, we want to like only lemmatize nouns, verbs, adverbs, and adjectives. Anything else gets discarded. And I already rerun this for you in advance, just because it takes a long time. As an alternative, if you had a very big data set, for example, right now we only have 11,000 records, about 11,000 records. It took like about 4 minutes to lemmatize all of those like documents and tokens and words that we had. You could use stemming. However, that, as I mentioned, uses a very a heuristic way to just truncate the words rather than actually give you the right words. So it might give you strange words within your topics at the end. So if we look at what this this might look like, for example, is this is some example. It's like some of these words that we had previously got removed because they like the lemmatization did that based on these bigrams, and then based on that we can now move into, let's say, the actual modeling. So in here we will use a library called TomatoPy, which uses a specific type of Bayesian inference method called collapse skip sampler that you can check on the article. But I just want to mention here as a side note, there's a lot more documentation online about GenSim because it's a more commonly used library. However, I must say that their HDP model might not give you the best results with this data set specifically. I extensively tried to tune it, but I couldn't really get it to give me good results. Okay, so just so you can keep something in mind, I just want to show you this image, which is the hierarchical Dirichlet process, kind of like plate diagram. And so you can see how this gamma parameter up here kind of influences this kind of overall topic distribution that then gets shared across the specific documents, as an example G1 and G2, and these concentrations on these documents gets defined by a parameter called alpha. Okay, now taking that into account, the first thing you want to do is you want to create a object, a topic model object with TomotoPy. You need to specify how you want to weight the terms, and here I'm trying to downweight the terms that appear in high frequency and upweight the ones that are less frequent. And here I'm pretty much saying remove any words that don't appear that appear in less than 5 documents. And here I'm removing the 7 most frequent words. And as I mentioned on top, gamma 1 allows it to be quite the concentration to be quite diffuse. So basically, I'm saying let the document share a lot of topics, and then alpha 0.1 means like I'm saying that the documents share a lot of topics, but individually each document has only a very few amount of topics. So basically, reducing that parameter makes it more concentrated. So less spikes, as you can see in G1, G2 might be expected compared to this G0, which has a lot of larger spikes. Okay, I also want to initialize the number of topics. I'm assuming there's 10 topics, and I can set a seed. Okay, so once I initialize the model object, I need to add the actual tokens, and you can do this by using the method addDoc. And then you want to set up something like the MCNZ burn-in, which basically completely removes or weights 100 kind of like iterations or samples to then collect the data, because you're assuming that this will give you better results. And so if we just very briefly run this cell, it tells you this is the number of documents, this is how many, this is our vocabulary size, so unique tokens, and this is the number of tokens that we have, as well as removing the top 7 words. Obviously, if I change this to 6, then this will give me only 6 top words. Okay, once I've done that, now I can actually train the model. I want to train it over 1,000 iterations, but I want it to only be printing out every 100 iteration. And you can do this with this for loop, and the training is just using the train method. You can also specify the number of workers you want to be using to train the model. And so if we wait here for a second, it'll start printing out both the likelihood per word as well as the number of topics that are alive. I'm not going to go into the details of what does that mean because that is part of how the method works. Basically, it creates topics, and then if a topic doesn't get assigned to any word, then it just gets destroyed. But it keeps kind of like taking topics from the shared distribution up here. So as you can see down here, it's printing out the log likelihood per word, as well as the number of topics. From the beginning, after 100 iterations, if you want to call it that way, it already has 22 topics. And so it'll keep printing out as we move forward the number of topics. And these normally is a good way that you can use to double check that there is learning happening, because if you don't see really the log likelihood decreasing or increasing in this case, or the number of topics changing, then that might give you some indication that your model isn't training. So at least in this case, we can see that the log likelihood is decreasing. It seems that we're just going to wait a little bit for this model to run. Okay, so this ran. The number of topics got stuck at 22. That means that is what it found to be the optimal number of topics based on our initial set of topics. However, you can see that the log likelihood actually increased, so that means that the model was learning. It's marginal, but it still was learning. So how do you get the topics? In my GitHub, you can find this function, but basically what it does is it goes through the trained model, gets kind of like the counts of how many words were assigned to each topic, and then basically outputs a dictionary with the most, the top 10 words for each topic. As an example, this is topic number 1, which is government, belief, law, and you can see what are the frequencies. This is another topic, topic 0. This seems to be a topic about space. You can see the words and you can see the frequencies. Okay, so now that we have that, we want to evaluate, how well is our model doing. And one of the things we can do is we can use a coherence. You can see the reasoning behind the coherence in the article, but basically here we can use the GenSim corpora and GenSim coherence model to compute this. So first what we do is we create a vocabulary based on the initial set of tokens. Then we build the corpus in a way that GenSim is able to understand it. And then what we do is we want to get like turn our initial dictionary that we have here into a list and only extract let's say the words from those topics. So we can run that, and as an example, here is kind of like what we get out of this loop that I constructed above here. Okay, so what you can do now is you can build a coherence model with a GenSim function. You can pass this topic list, you can pass the corpus that we just created, the vocabulary, as well as the actual tokens that we had. And then we can specify how to compute the coherence. In this case, we're going to use the CV coherence. The reasoning is because it performs the best type of, it's the best metric that we can, the best way to compute the coherence metric. It uses sliding window to compute this probability of co-occurrence across documents. And so we can do that, and we can use the getCoherence method to actually compute it. And as you can see, we're getting a coherence of 0.6, which is considered to be a good coherence, which is telling me that the topics, all the topics that the model obtained seem to make sense, in that these words, for example, appear together quite often across all the documents and within a 100-word sliding window. Okay, so now that we know that the model or the topics are coherent, we might want to do something that is hard to do in datasets where you don't have true labels, but we can do in this one. So what we want to do is we want to, let's say, get the first document or the first set of tokens from the first document. Then we want to create this document instance, which basically we can then use to kind of like ask the model, hey, try to infer what topic is most likely the topic of this document. So if we run that, it says that it's topic 7. So then we can go into the model and see what the topic 7 is. And it says like, oh, it's, this is what the topic looks like. And you're like, okay, car, key, bike. And then if we go back into original data, you can see that the topic name is recommendation autos, which pretty much correlates here with the type of inference that the model made. I want to make a side comment here is, if you don't have topic names or true labels for your data, you can always still do some kind of inference and do some sanity checks here. So you can, for example, assuming that we don't have the topic ID or the topic name, you could actually get the content, try to make some inference, on the train, see what the model gives you, like what is the most likely topic that is produced by, or would be inferred by the model, and then look at the content and make sure that that makes sense. Because sometimes this might be really good, but in the end, the inference, or if you were to throw it into an unseen document, you might be getting something that is not correct, and it might be inferring an incorrect topic. Okay, so here's another thing you can do. On my GitHub, link to the article, you can find this word cloud functions, where basically what it does is you just pass the model and the topics, and it very neatly will grab all of the words within the frequencies within each of the topics, and then it'll print them out so you can like see them and then compare them. For example, this is like the science space topic that is part of the 20 News Group data set. There's other ones that don't make a lot of sense, but there's others such as these ones that could be about sports, Raiders and Steelers. And so those are things that, you can easily check visually whether it makes sense. So just to finish up, I mentioned a couple of cautionary tales in the article, and I'm gonna kind of like show you what I meant on cautionary tale number 3, which is that you might get different results based on different methods. And so in here, I'm going to show you what happens with, in this data set with Gensim's HTP model. This model is based on a method called online variational inference, which is it's basically a Bayesian inference method that rather than sampling directly from the target distribution, what you're going to be doing is you're going to be approximating this target distribution with some kind of a simpler distribution. The main advantages here is that you have lower cost in memory because you don't need to be collecting the samples, and you can also increase in terms of the speed, because specifically this method, online variational inference, allows you to do some kind of gradient optimization with a somewhat of a mini batch, randomized mini batch, which, if you have millions of documents, you might want to only get a couple and get an approximation with that, rather than having to go through the whole million documents to do the inference. Okay, so with that said, this is basically, again, building the vocabulary and corpus for the Gensim model. And here I'm fitting 3 models. And how they differ is based on the kappa parameter. The kappa parameter pretty much kind of like manages the learning rate, meaning like the gradient updates. You can think about this as somewhat as a gradient descent related algorithm. And so you can think about this as the learning rate at each iteration or each step. And this has a decay kind of like factor. Here is a Heroku Dash app that I built, where you can like kind of see how these parameters influence the learning rate. For example, if kappa were equal to 1, this is kind of like how it would look like. If kappa were 0.6, or tau would like change to 0.1, then these would change. Unfortunately, it's not showing right now, but here's an example. You can see how like that learning rate kind of like is less pronounced as whether kappa is equal to 1. It becomes quite pronounced, and you have a very small learning rate very early on, versus a smaller kappa gives you a lower learning rate further along. So it pretty much has to do with how you're updating or approximating the distribution. Okay, so if I run that, it'll take a quick second. The gamma and alpha parameters, I'm setting them up the same as I did previously for the TomotoPy package. Now the T and the K are basically ways in which you're truncating the possible numbers of topics to consider at each level. T is truncating this global shared number of topics, and then K is truncating the possible number of topics to consider at the document level. So again, this is saying consider 30 overall topics, but then I'm saying individually on each document, you might have up to 8 as an example. And so another thing that I want to briefly mention while that is running, this is why it's important to always check, like the topics, is you can see here that there's a couple of topics that clearly don't make sense, but regardless, the coherence told us that we had a very good coherence in the model of the topics. So it is important to do like a sanity check and not just trust these metrics or statistics, because in a lot of the times we might just go with a flow and find out that it was the model wasn't doing that great. It was just some one-off circumstance in which we were getting, by how this is computed, a good coherence. And so right now it already fit the model, the 3 models at the different kappa values, and now it's evaluating the coherence of each. So we can see how these change as we change kappa, as an example. And this will take another second, just because it's computing, it's doing some data augmentation as part of this computation of coherence on how it's treating the documents, because it's using this sliding window of 100 words. Okay, so let's look at the results. So it seems that the variational inference model with a value of kappa equal to 1 gives us the best coherence. And so we might be like, yes, this is probably the best model, but actually let's look at how this looks like. We can use the PyLDAVis library to kind of like get a sense or analyze these types of topics. This is one nice integration that this package has with Gensim, which doesn't exist with TomatoPy. However, it is very useful to double check what's happening. So for example here, this is telling me, as you can see, there's a lot of these other smaller topics. It has up to 30 topics. However, if I were to ever do some inference in a non-scene document, this model will most likely assign this first topic as the most likely topic. And as you can see on the words on the right, it's such a generic topic. It says article, make, think, get, time. So we really can't make any inference. Maybe here, as we look into these smaller topics or less represented topics, maybe we might be able to get, we might be able to better capture the original 20 newsgroup dataset topics. However, just because the amount of weight that is put into this, let's say, topic, because it's so common, the model will always infer as the most likely topic this, just because it's so general. Okay, well, with nothing else said, thank you for watching. I hope this was helpful. And if you have any questions, please post your comments, reach out to me through Twitter, or look at my GitHub if you want to play around with some other examples. Thank you very much, and hope everybody has a good day.